Hey guys, welcome back. In this continued series of pipe design, Casey's going to walk us through the C3D pipes and using storm sewers to generate our hydraulic grade lines and to refine our pipe system using those hydraulic grade lines. So let's learn.
Welcome back, guys. This is Casey. We're going to be continuing our C3D pipe series. Where we left off last, we had just finished completing our profile and using our profile to finish designing our pipes and structures. Between that video and this one, I went ahead and cleaned up the proposed grade surface and fixed some of the errors there, just with some basic surface troubleshooting. So now what we have here is we have a profile that is almost finished, not quite finished. But we have a profile here that has all of our pipes and structures as well as an updated existing and proposed grade surface. And what we're going to do in this video is we're going to take this profile, we're going to get it on its own sheet and get it complete and ready to go so that we can send our profiles to our jurisdiction, and we'll have a well-designed pipe network with profiles that show off that we meet their cover requirements, we meet hydraulic grade line requirements, and that we can pass the required storms that we need to pass. So we're going to start by just taking a quick look at our profile, see what we're missing here. So one of the things that I noticed right off the bat is that we can't tell which one of these lines is the existing, which one's the proposed surface. One of the things I like to do is I like to change the existing line. I can just go ahead and I can change the line type to be a dashed line, right? So that can be our existing grade surface or something similar to our VG layers. You can change the layer of this itself to one of the VG layers, like the VG Topo Minor 2, which you can see is also on the Dash 2 layer. But I usually just change the line type. And then this proposed grade surface will just stay a solid line so that you can kind of differentiate between the two. And then we like to label them, so I'm just going to go ahead and do T for text, and I'm going to punch in a little bit of text, and we're going to type in proposed grade. Go ahead and drag this guy out. And existing grade. Right, and we're just kind of find a good spot along the profile to label these guys, right? So the existing grade label might be best, maybe right here. So we're just going to go ahead and rotate this guy to be roughly the same angle as that existing grade, so it kind of sits on it nicely. Then the proposed grade, we can just kind of drag and drop, do the exact same thing on the proposed grade profile. Like this, just like that. Now when you look at the profile, you can tell which is the proposed grade and which is the existing grades, and that's great. Now we've got that labeled. We can kind of just move around our labels and such, make sure everything's nice and neat. Not a whole lot of clutter. Whenever you're designing sheets or profiles or really anything in Civil 3D or CAD, the key thing is legibility. You want everything to be clear, legible, so that reviewers or other design professionals can look at the work you've done and they can tell what's the intent, what's actually being designed, how it's intended to work, will it work. So presentation is key. So we want to make sure our profile is nice, neat, clear, clean, easy to read, etc. Okay, so now the only thing that we're missing here on our profile is our hydraulic grade lines. So our hydraulic grade lines essentially use a bunch of different variables that we're going to have to input in order to show what the water level will be at under a certain storm event. So typically the storm events that we design to are the 25-year and 100-year storms. What does that mean? Well, in any given geographical area, we have rainfall data for hundreds and hundreds of years, and we can use that rainfall data to pick out how often we have extremely bad storms. So a 25-year storm would be the worst storm on average that's going to occur at a specific geographical area. So, and it's the same thing for a 100-year storm and so on. So out somewhere where they get much less rain in some sort of more arid desert area, you're not going to have to design really big, huge stormwater systems to accommodate a bunch of water because they simply don't get that much rainfall and don't get that much stormwater. In another area, in a jungle, you might get rainfall every single day of the year or half the days of the year. And so they have to have really large stormwater systems to accommodate all that water. So we're going to have to go and we're going to have to find the rainfall data for our geographical area and then input that along with some other key points of data in order to generate the elevation that our water will be at in our pipes under a given storm event. Okay, so what are the design requirements that we're looking for from our hydraulic grade lines? We're looking for two things. Typically, the main requirement is going to be the 25-year storm has to be retained within all of the pipes, meaning the water has to stay basically below the crown of each of the pipes, and it can't pool up into the structures. And the 100-year storms are meant to be contained entirely within the structure, so they can completely fill up the pipes, and then they can sort of pile up, and the water can pile up inside each of the structure. However, it can't surcharge out of the structure. So if you ever driven down the road during a really bad storm or right after a really bad storm, you might run into a catch basin or an inlet or manhole that has water just puddling around it, or water surcharging out of the structure. This is obviously bad. The intent of stormwater systems is to make our roads safer and to not to prevent flooding, to prevent damage to property. So we don't want any water surcharging out of the structures, even under the 100-year storm, which is going to be a pretty intense storm. Again, only occurs on average once every 100 years. Okay, so how can we do this? Well, the first way that I'm going to show you guys how to do this is using another software which is attached into AutoCAD Civil 3D called Storm Sewers. So what we're going to do is we're going to come to the Design tab here. We're going to hit this little drop down, and you can see you can launch Storm Sewers, and you can also hit this guy here, Edit in Storm Sewers. We're going to click this guy right here, and then it's going to ask you which of your pipe networks you want to export. So we've only made that northern network, that Storm A network thus far, so that's the only network we're going to be able to export. So I'm just going to go ahead and export that entire network. Okay, and then we're going to have to pick a spot to save it. So I'm just going to go ahead and navigate to this project. And then we're just going to go ahead and find our stormwater file or hydrocalcs file. We'll make a new folder for our HGLs. Then we're just going to save this .stm file here. We'll just give it the name of the project, or sorry, the project number, and then HGL with today's date. Hit save. Okay, and this is going to open up our Hydraflow Storm Sewers extension for Civil 3D. And as you can see here, it has our pipe network mapped out. Obviously, it looks very different from CAD, a little bit simpler, but it's got all of our structures and pipes that we chose to export into this file. And if you click this little Pipes and Inlets tab, you'll see this huge table with a bunch of information, a bunch of data, a lot of which we're going to have to input. And then once you run it, it's going to output a bunch of results. And then under this results tab, you can generate custom reports. It also has a bunch of different templates that you can use for reports, like DOT or Florida DOT. This Florida DOT one is very, very similar to the table that Florida Department of Transportation requires you to output if they're going to be reviewing your profiles and stormwater system. So some of these templates are really useful, and you can also click My Report here and this little three dots here, and you can essentially make a custom table with whatever values you want to show off in your table. So now we're going to want to import all of the important data about our pipes and our inlets. So I'm just going to go ahead and navigate. Let me declutter my screen here for a second. I'm going to go ahead and I'm going to navigate here to our profile, where we can kind of look at all of our inlets, and we can punch in a lot of the key information. So the first thing you'll notice is that for the pipes, when you export them, it actually already includes your invert elevations, your slopes, the size of your pipes, your line span and rise, the line type. So it's the circular pipes, 18 inches or 1.5 diameter pipes. It already includes the in value, so this is the correct in value or Manning's number for HDPE pipe. You might have to change this value if you're using a different type of pipe. The in value, which is essentially a coefficient, sort of like the coefficient of friction for the pipe, right? Like how smooth is the pipe, how smoothly will water flow through the pipe is going to be different for different materials. So HDPE is very smooth plastic, whereas if you use concrete or corrugated metal pipe, those values are going to be different. So that's something that you might have to change depending on your pipe material. Okay, and then all of this information here, your known Q, drainage area, and runoff coefficient are the most important pieces of information which are going to input into this table to generate your HGLs. So what does this mean? Well, we use what's called the rational method, and the software uses what's called the rational method to calculate how much water is entering into each structure here. So I'll just go ahead and pull this up so I can draw it out. The rational method is Q equals CIA, where Q, or known Q, is a flow value in cubic feet per second. C is a runoff coefficient. I is rainfall intensity, and A is the area in which you're calculating your Q value. So as you can see here, these three values here, we have a known Q, so that's if you already know what the flow is through that pipe. And you might know this because of, you might be calculating the flow out of an OCS for the pond. So in a different software, it might calculate what your flow out of the pond is through your OCS. So that might be a Q value that you already know. In our case, we don't have any known Q values, so all of our Q values are going to get generated through a drainage area, runoff coefficient, and intensity value calculation. So we're going to have to input this CIA. So our drainage area is pretty simple. You're going to have to find and delineate the areas that drain into each inlet. So we're just going to go ahead and go back to our plan view here on the bottom of our screen. And we've actually already done this in our CZ Hydro Storm. You can see here, these red areas are the drainage areas going in to each inlet. So this area right here in the corner drains into this guy. This area right here drains into this guy, and so forth all the way down, right? So we can grab these little areas we've delineated, run AAA, find the acreage or the square footage. So this is something that we've already done. If you haven't delineated your drainage areas yet, you're going to have to look at your proposed grade surface, and you're going to have to basically interpolate your proposed grade in order to determine where water is going to go, and that way you can draw out certain drainage areas. That's a topic to discuss and cover in another video. So we have these drainage areas defined, right? Now we have to pick out our runoff coefficient for each one of these drainage areas. So runoff coefficient is essentially an estimation of how much impervious area is in that drainage area. So your runoff coefficient is going to be much higher if you have an area that is almost entirely impervious, right? So if you have an area that's 95+% impervious, your runoff coefficient is going to be 0.95. If you have an area that's, say, 50% impervious, your runoff coefficient is going to be something like 0.65. If you have an area that's only 25% impervious, your runoff coefficient might be 0.35, etc. So your runoff coefficient is going to be higher for more impervious areas and lower for less impervious areas. So once you punch in your runoff coefficient and your drainage area for each one of your inlets, you're going to click this little IDF button here, and then you're going to either open one of our IDFs that we already have saved. So as you can see here, under Support, Documentation, Stormwater Hydro, Pipe Design, and IDF files, we have a bunch of IDF files that we've already saved, and we also have more under Hydrographs, and then here is a bunch of IDF files outside of the state of Georgia, and within the state of Georgia where we do a lot of our work, here's a bunch more IDF files for specific geographical areas. Right? So if you don't have an IDF file for your specific geographical area, what you're going to have to do is you're going to have to open up your browser, and you're going to have to navigate to the NOAA Atlas 14. So you can search up NOAA, NOAA Atlas 14. Click on it. These are all the states which NOAA offers rainfall data for. So we're just going to go ahead and select Georgia, because this is where our project that we're using for this demonstration is located. Okay, and then you can search the location by the address of the location as well as station or latitude and longitude. So I'm just going to go ahead and look up the city of Lafayette, which is where this is located. Okay, just going to go to maps here, and I'm just going to grab something that's somewhat near where our site is, anything random, copy the address, and then we can just drop that in here. And then we can go ahead and select precipitation intensity so that our values for precipitation are given to us in inches per hour rather than inches. And then this is going to be the rainfall data table that NOAA is going to spit out for you, which you can then input into your storm sewers on your IDF table here. So I'm just going to go ahead and close out of this so I can move this window off to the side here. I'm going to open this IDF again. Right? And then you can select IDF table here, and then you can punch in all of these values, fill in as much as you can based off of the available NOAA rainfall data, right? So we can just go ahead and start here for a 1-year storm with a duration of 5 minutes. We have a value of 5.00, and we can just go ahead and continue down. So 2.98, 1.99, 1.30, and we're just going to continue to do this basically to fill out the entire table. And then the NOAA rainfall data does not offer 3-year storms, so these are, you're all just going to leave as 0. Okay, and our last one here. Okay, and once you punch in all the values, again, if you don't have that geographical area saved already in our documentation, it's great to save it for later use. So we can just go ahead and hit save here, and then we can save it under the support documentation. IDF files, we have more located here under the documentation, stormwater hydrographs. And this is located in Georgia, so I'm just going to go ahead and save this as Lafayette.idf, save, and as you can see, it's Lafayette.idf now. Okay, and then we'll just go ahead and click exit. So now we have, out of our Q equals CIA, we have our I entered, right? So that intensity rainfall data has already been entered, right? That's what we just did from this NOAA data here. Okay, now we have to punch in the drainage area and runoff coefficient for each one of these inlets here, which we already pointed out. And once we do that, there's a bunch of other information that we have to fill out about the pipes themselves. So we're just going to go ahead and go over this information about the pipes themselves here. Inlet time is going to vary on a handful of different things. You can get CAD to output certain inlet times based off of your surface, or you can do calculations at each specific inlet. A lot of jurisdictions are going to require that in your post condition, your inlet time be 5 minutes. So I'm just going to go ahead and punch 5 minutes in for each one of these inlets, and I can copy this value and then just hit the down arrow on my keyboard, and I can paste it in to each one of them and hit enter. Okay, so once you've punched in your either known Q or combination of drainage area and runoff coefficient, that's a key point that I just want to reiterate. If you have a known Q value in a certain pipe, you don't have to punch in a drainage area or runoff coefficient value, right? You punch in your drainage area and runoff coefficient values, which are then used in conjunction with the rainfall intensity data that you punch in under your IDF tab to generate a Q value for the pipe. So if you have a known Q value already, those other 3 numbers, drainage area, runoff coefficient, and rainfall intensity, are not needed. So there's no point for you to find the drainage area or runoff coefficient of, say, the OCS of your pond or some other structure in which you have a known Q value for. So in most scenarios, you're going to have a known Q of 0 for many of your structures, and then you're going to have some value for drainage area and runoff coefficient in all of the places where you have a known Q of 0. And then the places where you have a known Q, say a value of known Q equals X, you're going to have a drainage area of 0 and a runoff coefficient of 0. You have to provide either a known Q or a drainage area, runoff coefficient, and intensity data. So once you've done this, you're going to want to navigate to your inlets area, which you're then going to punch in a bunch of information about the inlet or each individual inlet. So one of the things that I want to discuss before we talk about the inlets and the pipes here is why we named our pipes the way that we named them, right? So if you remember in one of the earlier Civil 3D pipe videos, I discussed the naming convention that we use for pipes. So we always name our pipes in accordance with the most upstream structure that pipe is connected to. So for example, here at our outfall, right? This outfall structure is our structure A0, or our outfall. This pipe here is not named pipe A0, it's named pipe A1 in correspondence with the upstream structure that it's connected to. So this is structure A1, and if I select this pipe, drag over my properties pane here, you'll see that this is named pipe A1. So now, when we export into our storm sewers, our names are gonna get exported with all the other information under line ID. So the reason why we do this is so that when we're punching in our drainage area and our runoff coefficients, right, pipe A2, the area that drains directly into pipe A2 is the water that enters our stormwater system at structure A2. all of the water that enters into our stormwater system at structure A1 is going to flow immediately downstream into pipe A1. So that water is never going to enter into pipe A2. So that's why we name our pipes in correspondence with their most upstream structure. Again, this is very critical. All of the water that's going to enter directly into pipe A4, which is this pipe right here, okay, is going to enter into this pipe from its upstream side, structure A4. And all the water that enters into structure A4 is going to immediately flow downstream into pipe A4 and not upstream into A4.1 or A5. Right? So because in this software it asks for drainage area and runoff coefficient to calculate the flow that starts in the top of that pipe rather than the drainage area and runoff coefficient to calculate the flow entering in at the structure, we have to name our pipes and structures this way. Okay, now once we're at our inlet tab, we're going to go ahead and punch in a ton of information regarding each individual inlet. So all of these inlets here across this entire length of this pipe are catch basin inlets. So that type of inlet is going to be a curb inlet. So we're just going to go ahead and change our inlet type to curb inlet for each and every one of these. So we're just going to click this little drop down menu, change it to curb inlet. Okay, and as you can see here, there's a bunch of different options. We have manholes, curb inlets, grade inlets, combination inlets, generic inlets, head walls, drop curb, drop grade inlets. These don't make a huge difference. Some people will elect to have manhole as the inlet type for each and every one of their inlets. If you want to do that, you can do that. You're just going to have a little bit less accurate results. If you want to be more accurate, you can punch in the curb inlet, but generally the results are going to be very, very, very similar. Okay. Now, location is going to be either on grade or sag. It's important you understand what these terms mean. So on grade means that the inlet essentially follows the grade of the area that it's located on. So because all of these are catch basins, they follow the grade of the road. If an inlet location is sag, that means that that inlet is located at a local low point. So if water is flowing into this inlet located at a local low point, and the stormwater system gets backed up, the water will start to form a puddle in the road. If the road has a low point around that inlet, it'll form a puddle. If the location is on grade, if water cannot enter that structure because that structure is full, it'll simply continue to flow along the grade until it enters another structure downstream or flows off of our site. So because all of these catch basins here are along this main road here and none of them are designed to be at local low points, they're all going to be on grade location, which means we have to enter a bypass line number, or essentially what structure, if water cannot enter in at structure A2, where's it going to go? So we'll go ahead and start upstream. If water cannot enter at structure A7 because it's full, then where's the water going to go? Well, if water starts to puddle up here in the gutter in front of the structure here, it's going to continue to flow down the road on this side of the gutter until it reaches this structure here, which is structure A4.1. which means the bypass line number has to correspond to structure A4.1. Well, the line number in our software for structure A4.1 is 8. So the bypass line number for structure A7, which is the one that we're looking at here, A7, is going to be number 8. Let's go ahead and punch 8, right? So we're going to have to do the same thing for each and every structure, right? So for structure A6, if water starts to come out of the structure here, it's going to continue along the gutter until it enters into either structure A5 or structure A4. Well, the gutter here is probably going to enter into structure A5. It depends on how specific. We don't know the specifics of the grading here for this situation yet, but I'm just going to assume it's going to enter structure A5. So the bypass line number for structure A6 is going to be 5. Okay, and then for 5, if water starts to pool up here, the road's sloping again this way, so it's probably going to enter into structure A4. So the bypass line number is going to be 4. For A4, if water can't enter in the structure, it's going to fall along the gutter until it gets to structure A3. A2, or excuse me, if water can't enter into structure A3, it's going to follow along the gutter until it enters into structure A2. And then if water can't enter into structure A2 because this road is continuing to go down this way and we don't have any more inlets to pick up that water, if it cannot enter into structure A2, it's simply going to continue along the gutter of this road until it exits our site. So the bypass line number for structure A2 is going to stay off-site. For A1, it simply enters the pond, so you can leave the bypass line number as off-site, even though, or excuse me, if the water cannot enter into A1, it's going to continue along the gutter, and then it's going to follow along the road until it exits off-site, so it's also going to remain off-site. A3.1 is going to continue along the gutter until it enters structure A1, so A3.1's bypass line number is going to be 1, and then A4.1 is going to continue along the gutter until it gets into structure A3.1, so A4.1's bypass line number is going to be 9. Okay? Now we have to punch in a bunch of other data. So the road cross slope is going to be what's the cross slope, essentially what's the slope of the cross section of your road. So it's typically 2%. That's almost how we always design our cross sections, our assemblies for our corridors, etc. So this value of 0.02 we can leave alone. Our gutter cross slope for our gutter detail that we specify, our gutter cross slope is 8% and not 5%. So this value is going to change from 0.05 to 0.08. So I can just go ahead and copy that value all the way down. The local depression for catch basin inlets, the detail that we provide is 4 inches. So I'm just going to go ahead and type in 4 for all of these. The gutter width for our gutter here, as you can see, we can measure our gutter width is 1.5 feet and not 2 feet. So we're just going to go ahead and we're going to punch in 1.5 as opposed to 2 feet. And then the longitudinal slope of our at each structure is the longitudinal slope of the roads, right? So this varies depending on the location on the site, right? So some structures are going to have a much higher longitudinal slope, and some structures are going to have not quite as high of a longitudinal slope. So we can go back to our profile here, and then we can kind of see what the slope is at each structure, right? So we can go ahead and we can add profile labels, and we can select lines, standard, add, apply, okay. We're going to change our annotative scale back to 1:1 just so we can see. And as you can see, it provides these slope values here along our proposed grade, which kind of show us and give us an idea of what is the longitudinal slope on the road, right? Because all of these pipes and structures are located along the road here. So what's the longitudinal slope along the road that's flowing into each structure, right? So I'm going to go ahead and I'm going to open up my storm sewers again. And as you can see, we're going to start from structure A1, which is this guy right here. So those labels are really small, labels get really funky, but flowing into that structure, we've got about a 1% slope. So we can change the longitudinal slope to 0.01, and we can just go ahead and work our way up the list. So A2 here has about a 15% slope, which is going to be 0.15, which is probably going to get changed. It's probably not actually the slope of the road because that'd be extremely steep. So we'll be on the lookout to change that to get a more accurate number later, but we're just going to punch it in for now. A3 has about a 2.5% slope. A4 has about a 0% slope. A5 here has about a 9.7% slope. A6, we're just going to leave at 0 since it's got a negative slope that's flowing into A7. So that's a funky grade thing going on there. We'll just leave it at 0 for now. And then A7 here is kind of the same deal, so we're just going to leave that alone. And then A4.1 and 3.1 are not on this profile, so we're just going to go back to our plan view just to take a look at them. A4.1 again is across from A4, so what's the slope at A4? It's probably going to be the same as the slope at A4.1. So we're going from 880 to 870. So this looks like about a 10% slope. So we'll just go ahead and punch in that 0.097, close to 10%. And then our A3.1 is same deal, 866 to 860. And it's right across from A3, so it's probably going to be the same as at A3, which looks like about 2.5% slopes. Let's go ahead and hit enter for all those values. Okay, and then our gutter end value is going to be the Manning's number for our gutter. We have concrete curb and gutter. Usually we leave this number alone at 0.03 or 0.013. So obviously your Manning's end value is going to depend on the material of whatever the water is flowing through. So in this case, it's the gutter. Okay, so now we have all the values filled out. except for our drainage area and runoff coefficients. We have all the values filled out for our pipes and inlets. So now we're ready to just input our drainage area and runoff coefficients and then run our Hydraflow storm sewers in order to output HGLs. In order to establish the runoff coefficients that we're going to punch in for each individual inlet, we'll have to have our drainage areas already delineated. So once again, as stated before, you're going to look at your proposed grade, and you're going to look at all of the infrastructure that's being put in, like the road, where the gutter is, etc. And the more you do this, the more you'll be able to do it more accurately. But accuracy isn't super important here. You don't have to know exactly where every single drop of water that lands on the site is going to run off to. You just have to get a general idea of what the acreage is draining into each inlet. So once you have your drainage areas delineated, you can look into each drainage area and kind of just estimate the runoff coefficient based off of the amount of proposed impervious in that area. It's extremely tedious. It takes an extremely long time for you to calculate the exact amount of impervious in each individual drainage area, and then use the different types of imperviouses, find the slopes across the different impervious and pervious areas to determine a super specific runoff coefficient. So just in order to save time and to get a 95% accurate estimation of the amount of flow coming off of that area, we're just going to use sort of a set of estimations based off of the imperviousness of the area. So if I just go ahead and open up a notepad just to kind of spell it out for everyone. If we have impervious percentage as well as our runoff coefficient C, right? So you might have an impervious percentage of 180, 75, 50, 25, and 0. And each one of these might have a C value of 0.95, 0.83, 0.80, 0.65, 0.50, and 0.35. So this is the table that I use in order to estimate the C value or the runoff coefficient value for a given percentage of imperviousness within a drainage area. So I'm going to go ahead and move that off to the side for my reference. So I already went ahead and I punched in the acreage as well as the C value for each of these drainage areas for our northern Storm A pipe network. And just to take one as an example, if you look in this top left corner here, this is the area that's draining into this inlet right here, which is our inlet A7. I'm just going to go ahead and change the annotative scale just so you can see again. This is our inlet A7. So this area is, if I go ahead and grab this little drainage area that I've already delineated and run AAA, you'll see that it's 0.89 acres. Right, and then just taking a look roughly at it, the only impervious area is this small little portion of the cul-de-sac in the corner, and then these two houses, and the rest of it is all pervious. So to me, that looks like roughly about 25% of the whole area is going to be impervious, which is going to give me a estimated runoff coefficient of 0.50. And so you just go through each and every individual drainage area, and you do that process. And then you're going to punch in all of these values into your storm sewers. So we're going to go to our pipes tab. And we're just going to go inlet by inlet. So our pipe A1 is going to be the drainage area and runoff coefficient that's entering in to structure A1. So we're just going to go ahead and punch in the drainage area for structure A1, which is 0.44, and the runoff coefficient of 0.50. For pipe A2, again, 0.44, 0.50. Right? For inlet A3 is going to be 1.01 acres and 0.50. For inlet A4, we're going to have 1.25 and 0.50. Again, pretty much all these are 0.50. There's not a lot of impervious area on this proposed development, and each one of them looks like it's roughly about 25% impervious for each one of the drainage areas. So for A5 here, which is this guy, same deal, 0.61 acres, 0.50. For A6, we've got 1.03, 0.50, and for A7 we've got 0.89 acres, 0.50, and then for pipe A 4.1, which is right here, we've got 1.06 acres, 0.50, and then for pipe A 3.1, we've got 0.71 acres, 0.50. Go ahead and hit enter. Now all those values are in. Again, if we had maybe a drainage area such as such as this guy right here, this drainage area down here on this southern pipe network. Nearly half of it is taken up just by the cul-de-sac, and then plus it might have some drainage, if we adjusted it and included this house. So that's definitely 50% or more impervious, so the value for the C would be 0.65 versus 0.50. And if you're doing other projects like commercial developments that allow for much greater percent imperviousness, then you'll probably have runoff coefficient values much greater, like 0.8, 0.83, 0.95, etc. Okay, so now that we've got this, all these values punched in, we're ready to run our storm sewers. So we can go ahead and hit this run button right here. And then remember, we're looking for the HGLs from the 25-year and 100-year storms. So we'll start with the 25 years. So we're going to change our return period to the 25-year. We're going to change the calculation options to enhanced modeling system. Okay, and then starting at our line number, we're going to want our starting HGL to be at crown. There are some instances in which you're going to punch in a custom tailwater. Say, for example, if you're working in a state that's very close to sea level, then you might have to punch in a custom tailwater versus starting the HGL at crown. But in most instances in Georgia and in most of the southeast that we do development, besides Florida, starting HGL is going to be crown. So go ahead and hit OK. Okay, so this is going to give me one error. The line 7 inlet is on grade, so the gutter slope must be greater than 0. So we're just going to go take a look at that really quick. So line 7, which is A7, our longitudinal slope here has to be greater than 0. So we'll just go ahead and make it 1%. We'll go ahead and run it one more time. Same thing with these guys. These are all on grade, so we're just going to make them at 1%. Okay, we'll go ahead and run. Again, 25-year return period, enhanced modeling system, and then our starting HGL is going to be at crown. Hit OK. All right, so you're not going to see anything happen. It's just going to run it. And then in order to see the output, which again we're looking for the HGLs, you're just going to go ahead and hit profile here. And this is going to profile all of your pipes and structures just like we did before in CAD, except now it has this red HGL line. And then in order to see the entire length of our profile, which should match the profile that we've made, so I'm going to go ahead and delete these slope labels just so we can look at this a little bit clearer. We're going to run from pipe A1 all the way up through pipe A7. So we'll hit this little refresh button. And as you can see, this is the exact same profile that we've created in Civil 3D, except now we have this red line for our HGL. So as you can see here, this guy is surcharging out of the structures on the 25-year storm. So we can just go ahead and state that we're either going to have to size up our pipes, our structures, or increase the slope. We're going to have to make some sort of design change in order to get these HGLs inside of the pipes and get the 25-year storm completely retained inside the pipes. If you look up here towards this area at the top, this area is pretty much completely retained inside the pipes, which is exactly what we want for the 25-year storm. But once you go further and further downstream, you're going to see that it's going to start to surcharge out of the pipes, which is not what we want. So we might go ahead and make a couple of edits, and just directly in storm sewers here, just to troubleshoot and see what we might be able to do, we can go to pipes and then maybe change our most downstream pipe to a larger size pipe. So we can change the line rise and span to, let's say, 24 inches, right? Hit enter and then run this again. 25-year enhanced modeling system, starting HGL crown, hit OK. And then go ahead and hit profile again, A1 to A7, and as you can see here, that made a drastic difference. We might have to upsize maybe one more pipe, maybe this pipe right here in the center, or maybe upsizing this guy from 24 inches up to 30 inches might go ahead and fix it for us. So again, we're just going to upsize this guy again, change the line rise to 30 from 24. We'll run it again. 25-year enhanced modeling system, starting HGL crown, hit OK, and then we'll go ahead and hit profile. And as you can see, from pipe A1 to pipe A7, again, makes a really big difference, but we still got water surcharging out of this structure right here. So this is kind of our problem point. So I'm thinking we might want to change this 18-inch pipe, this 28 linear foot 18-inch pipe, to a larger pipe as well. So we're going to go ahead and change, and that's going to be our line 2, pipe A2. We're going to change this guy to a 24-inch as well. Run it again, 25-year enhanced modeling system, starting HGL crown. Hit profile, and then pipe A1 to A7. And as you can see, when we upsize that pipe, we no longer have water surcharging out of the upstream structure A2, which is exactly what we want. So this looks great to me. I'm gonna go ahead and export this, and I'm gonna hit export, and then I'm gonna wanna match my horizontal and vertical scale to the horizontal and vertical scale of our profile in our model space within our thing, right? So we can't have our horizontal scale greater than 1 to 50. We can have it at 1 to 100, so we can choose to do one of two things. We can make this guy 1 to 100, but these labels are gonna get super, super big. We're just gonna give it a second to load. Super, super big. So we can probably work around this by moving the labels off to the side and whatnot. Or we might be able to downsize to 1 to 50, right? And I think that looks better to me. So now that we're at 1 to 50, our scale is 1 to 50 horizontal and 1 to 10 vertical. So that's what we're gonna input here, horizontal scale 50, vertical scale 10. Press OK. And then we're just gonna go ahead and we're gonna save this in the appropriate file location, so usually hydro calculations, HGL, and then I usually will make a folder for my 25 year. And I'm going to name this HGL the downstream structure dash the most upstream structure. So this is going to be A0 to A7. Okay, it'll give me a little notification that the export is complete. Cool. Now we're going to do the exact same for the 100-year storm. We're going to hit run. We're going to change our return period from 25-year to 100-year. Enhanced modeling system, starting HGL, crown. Go ahead and press OK. We'll hit profile. And then we're just going to refresh it. Pipe A1 to A7. And as you can see here, we're just barely not surcharging out of this structure here, and then we're just barely surcharging out of these guys right here. So we might have to size up one of these pipes, might be the solution to that. But if we size up one of these pipes, the HGL for our 25-year is going to change. So we're going to have to come back and re-export our 25-year. So just for time's sake, I'm going to go ahead and export this one, but more than likely you'd size up this pipe maybe right here to keep the water from surcharging out of this structure, maybe size this pipe up here to keep water surcharging out of this structure. You're going to make some type of design change to keep water from surcharging out of these structures. But I'm going to go ahead and export this again with the same scale, 50 and 10, hit export, and then usually I will make another folder for my 100-year HGLs because in this case we're only doing this for one profile, but even for this project there's going to be much more than one profile, so I usually split them into 100 and 25 years. Again, A0 to A7, save. Wait for the little pop-up that the export was successful. Cool. Go ahead and hit exit, right? And then we're just gonna move this off to the side here. And what we're gonna do is we're gonna go to our project. So I'm gonna go ahead and locate that file path that we just created, that HGL 25-year and 100-year. So I'll start with a 25-year. I'm going to go ahead and open up this DXF file, which you can open up in CAD directly. And then once it loads up, you'll get your cursor here and it'll be all black. That's just because it's super zoomed in. So I'm just going to zoom out here. And as you can see, there's our profile export. I'm going to grab the HGL, and as you can see, it's all separate lines, but I can run SSA, select similar, and grab all of them, and then hit J for join. And now I have one polyline for my HGL. And then I don't want to import this storm HGL layer. I want it to be on the 0 layer, so I'm just going to go ahead and move it to the 0 layer. And then I'm going to copy it from a base point. So I'm going to copy it from this 840 elevation here, and I'm going to paste it at the 840 elevation on my profile here. So I copied it from 840 at the very start, basically station 0, 0 plus 0, 0, and 840. So I'm going to paste it in the same spot. Cool. And now here's my 25-year HGL, which needs to get labeled. So I'm just going to go ahead and draw a multi-liter on this profile and name it 25-year HGL so that it's called out on my profile. And I typically like to choose really specific colors. I think these are the best colors that you can use for your 25 and 100-year HGLs. I typically pick color 150 here for one of them, and then I also pick color 70, I believe, for the other. These two colors plot really, really well. It's either 60 or 70. I believe it's 60 actually. So these two colors plot really, really well because oftentimes your 25-year and 100-year HGLs will be almost on top of each other and you can hardly tell them apart. So the reason I picked these two colors is because they appear very dark when you plot your sheet, but they're also very thin. So they're very thin and very dark. A lot of these other colors that have very thin lines are like gray and you can hardly see them. Like magenta has a thin line type, but it's very, very light, very, very light gray. You can hardly see it. But these two colors, 60 and 150, they plot very, very dark, but they're very thin so that when they're right on top of each other, their line thickness doesn't muddle them together. So I'm going to go ahead and I'm going to just select that color for that guy, just like that. And then I can close this guy out. Don't have to save it. Okay, and then I'm going to open the 100-year. Same thing. I'll open the DXF file. Give it a second to load. These files are quite slow to load sometimes. Zoom out. And then I'll grab this guy, select similar, join so that it's one big polyline, take it off of this storm HGL layer because we don't want to import that, and then copy it from station 0+00 and the elevation 840 or some other elevation that it has in common with our profile. And I'm just going to paste it in the same spot. As you can see here, they can be really, really close to each other. Of course, they kind of differentiate and separate themselves further up in the profile, but you know, when they're really close to each other and when you plot to a sheet and it's black and white, you're going to want colors that are going to be really, really dark and really easy to see, but also not muddled together because they're really thick lines. So I'm going to go ahead and select that color. And then same thing here, I'm going to just add a multi-leader to call out the 100-year HGL. Cool, I'll make that blue just so I can see that it corresponds. Cool, so now this profile has all of its labels for both the structures and the pipes. It has its HGLs that we did with storm sewers, and now it's ready to go on a dedicated profile sheet later on, but the profile itself is pretty much done, and you're going to repeat this process for each and every one of your alignments that you've created. So there should be a profile for every alignment such that every structure and every pipe is shown on your pipe profile somewhere.